Hello. In this video, we are going to look at differentiating and integrating a power series. So suppose we have a power series that converges to a function f on an interval. So then either we have that f is differentiable for absolute value of x minus a being less than r. Notice the interval will stay the same. And f prime is found by differentiating our power series. And differentiating this is that f prime of x equals, we are just using the power rule that x to the n, when we take the derivative, is n x to the n minus 1. C sub k is just a constant that doesn't have to do with x or n, or not in a differentiating way. But this x minus a to the k will come down, x minus a to the k minus 1. So here we just used the power rule. And it will be, the derivative will be equal to this power series for the absolute value of x minus a being less than r. What that says is the interval won't change, but the endpoints might. So we will need to recheck the endpoints if we find a power series by differentiating. We can take the derivative. We can also take the integral. The indefinite integral of f is found by integrating the power series. Of ck x minus a to the k. Recall the integral of x to the n is x to the n plus 1 over n plus 1 plus c. So we would do the same thing. The integral of f of x is dx is the series. The c sub k is just a constant. And then we will take this x minus a, add 1 to the exponent, and divide. Plus c. Still, interval won't change. But endpoints might. Because this indefinite integral is true for absolute value of x minus a being less than r, and c is an arbitrary constant. So let's take a look at an example. Still, the only function we really have is this 1 over 1 minus x being equal to x to the k. We want to find the power series and the interval of convergence for the following functions. We want to do the derivative first. So this is, we have our function which is 1 over 1 minus x. And we know its power series is the series k equals 0 to infinity x to the k. If we take the derivative, f prime of x is going to be equal to 1 over 1 minus x squared by the chain rule. I encourage you to make sure you know why that's positive and not a negative. And so if I want to find the power series of the derivative, I'm going to take the derivative of the power series. So the derivative of the power series is k x to the k minus 1 by applying the rule that the derivative of x to the k is k x to the k minus 1. So there is our new power series. And that means that the power series of the derivative is 1 over 1 minus x squared, which is equal to the series k equals 0 to infinity k x to the k minus 1. We also need the interval of convergence. This works for the absolute value of x is less than 1 or negative 1 to 1. We want to check, is that the same when x equals 1 or x equals negative 1? So when x equals 1, we have the series k equals 0 to infinity of k, and x to the k minus 1 is ultimately still 1. 1 squared is 1, 1 cubed is 1, 1 to the 100th is 1. So this x to the k minus 1, when x is 1, is just 1. And the limit as k goes to infinity of k is infinity. So this diverges by the divergence test. Because infinity is not 0. When x equals negative 1, we have the series k equals 0 to infinity of negative 1 to the k minus 1 times k, which also diverges by the divergence test, because the limit as k goes to infinity of negative 1 to the k minus 1 times k does not exist, which is not equal to 0. So when we took the derivative, the endpoints still diverge. Negative 1 and 1 still diverge. So f prime of x, which is 1 over 1 minus x squared, or is the series k x to the k minus 1. This is true for x in negative 1 to 1, or for the absolute value of x being less than 1. Now, something we want to note about this series is that when k equals 0, we would have 0 times x to the negative 1, or 0 over x. And at the center, 0, this is 0 over 0. We don't like this. So we'd really like to get rid of that term where we get a 0 over 0. So we're going to look back at the original series, which is this series k equals 0, x to the k. So f of x equals the k equals 0 to infinity, x to the k, which looks like x to the 0, we say is 1, plus x to the first, plus x squared, plus x cubed. And then when we take the derivative of this, we get the derivative of 0, or sorry, the derivative of 1 is 0. The derivative of x is 1. Then we have the derivative of x squared is 2x plus 3x squared. And then the next term would have been 4x cubed, and so on. Meaning this k equals 0 term, when we look at the derivative, is actually just a 0. We don't want it in our series because for how the series is written, we're getting a 0 over 0 term. But the derivative of our actual function is telling us that first term should be 0. So we can just remove it by saying, instead of starting at 0, let's start at 1. Because then, starting at 1, we will get this 1 plus 2x plus 3x squared. So this series is going to be k equals 1 to infinity, k x to the k minus 1, to get rid of that 0 over 0 term. So we can start our lower bound at 1. If we want to still start our lower bound at 0, we can also do that by what is essentially a u sub. If I want this first term, k, to be 1, even though I'm starting at k equals 0, I can say this is k plus 1, x to the k, by adding 1 to everything inside my series because I have removed 1 from my lower bound. So there are the two different series we could write to get rid of that 0 over 0 term. So our derivative series is this k equals 1 to infinity, k x to the k minus 1. For these still apply whether we start at 0 or we start at 1, meaning those bounds or the endpoints still don't change. So here is our formal derivative power series for 1 over 1 minus x. Now, our other example is taking the integral, and taking the integral is the same idea. If I have my function, which is 1 over 1 minus x, I can integrate that. And when I take the integral of this, I will get the negative natural log of the absolute value of 1 minus x for the integral of f of x dx plus c. But the power series for this function is the series k equals 0 to infinity x to the k, as we have known for a while. If I want to find the power series for this function, I can integrate x to the k. And I will get k equals 0 to infinity. Recall the power rule, which I will add 1 and divide by it. So this will become x to the k plus 1 over k plus 1 plus c. I don't need the plus c on both. So where we drop the plus c is actually from the function side, meaning we have the integral of f of x dx is equal to the negative natural log of the absolute value of 1 minus x, which is also the power series k equals 0 to infinity x to the k plus 1 over k plus 1 plus c. Two things still remain. One, we need to check the endpoints. We have that this is true for the absolute value of x being less than 1 or negative 1 to 1. So we need to check the interval of convergence for the integral. But before we check the interval of convergence for the integral, we also wonder, what is c? Can we make c a number and not just have an arbitrary constant? And the answer is yes. If we pick a convenient value that is already in our interval, say 0, 0 is already in this interval. It's also our center. So we know it's going to converge. I'm going to plug x equals 0 in, and I get negative natural log of the absolute value of 1 minus 0, plugging 0 in for x, equals the series k equals 0 to infinity, 0 to the k plus 1 over k plus 1 plus c. This series is just 0. And the natural log of 1 minus 0 is 0. So we get 0 equals 0 plus c. C is 0. So c is actually 0, meaning the power series for the negative natural log of the absolute value of 1 minus x is k equals 0 to infinity x to the k plus 1 over k plus 1. Last thing that we were just talking about is the endpoints. So if x equals 1, we get the series k equals 0 to infinity of 1 to the k plus 1, which is 1 over k plus 1. This is going to diverge by a comparison test with the series 1 over k. I'm going to leave that as something for you to try. But we can use the limit comparison test. We could also rewrite that series a little bit, because this is also the series k equals 1 of 1 over k, which it's now the harmonic. So diverges by the limit comparison test. Also diverges because it's the harmonic. In disguise. If x equals -1, then our series is -1 to the k over k for k equals 1 to infinity, doing that same switch of start this at 1 and remove the plus ones. This is the alternating harmonic, and the alternating harmonic converges. Meaning our new interval of convergence is still -1 to 1, but now that we've taken the integral, it will diverge at the endpoint of 1 by the harmonic, but converge at the endpoint of -1. So the interval itself stayed the same, but the endpoint changed. Next video, we'll take a look at one more example, seeing both the combining element and the integration element and differentiation elements come together.